Hey, this is Horner. We're going to look at the second part of Chapter 14 that deals with heat. This section deals with phase transitions. So this is whenever you have a material, for example, if you have water, you'd start off with ice. You'd have to heat that ice up to zero before you would melt it, and then it takes a while to melt it, or it takes quite a bit of heat to melt it. Then that becomes water. You have to heat the water up until it gets to 100, and then you convert that to steam. That takes a tremendous amount of energy, and then you can heat up the steam past 100 degrees. So during phase transitions, basically heat flow continues and internal energy changes, but the temperature of the two phases doesn't change. So right here you'll notice there's no temperature change, and you're going to notice there's no temperature change here either. So when you're getting that water up to 100, once it's all up to 100, you start to make steam. And until all that steam is gone, that water plus steam mixture remains at 100. Once you get it up, if you have it in a pressure cooker, you'd end up giving this more energy, and it would get above that 100 degrees Celsius point. So those are phase transitions in a nutshell. Different things, you'll see that the phase transition or temperature change from negative 25 to 0 is about 52 kilojoules. If you want to melt ice to go to water, it's 333, 419 to get it to go to 100 degrees, and then finally to boil it takes a tremendous amount of energy. So that's about 2,256. To get steam to go from 100 to 125 takes the least amount of energy, and that's about 50 kilojoules. So water is pretty important, as you already know, and so when we look at phase transitions for water, they're pretty important also. Latent heat is the amount of heat required per unit mass to produce a phase change. And latent heat can, for us, when we look at water, we're going to do latent heat of fusion, which is melting or freezing, and then latent heat of vaporization, which is turning it into steam. So for melting or boiling, the Q, the sign of Q, would be positive. For freezing or condensation, the sign of Q would be negative because heat is flowing out. So once again, if I melt or boil, the heat is flowing into the system. So I'm making ice go to water or water go to steam. That's positive. And then if I make water go to ice, or if I make steam go to liquid, then I am removing heat, and heat goes out of the system, so that would be negative. Like we said, if I'm going from a solid to a liquid phase, we call that latent heat of fusion. So fusion, you can just think of making a solid or taking a solid apart. And then vaporization, latent heat of vaporization, this would be making sure that we have anything going from liquid to vapor or vapor back to liquid. So those are the two different latent heats that you'll look at. When you have a substance in a solid form, there is a pretty strong bond that hold them near fixed equilibrium position. So energy has to be supplied to break those bonds to change that solid into a liquid. So when the substance is changed from liquid to a gas, there has to be energy used to separate the molecules from the loose bonds holding them together and to move those apart. So that's the microscopic view of what's happening in a phase change. Temperature doesn't change during these transitions because you're changing the kinetic energy of the molecules is not changing. So instead, your potential energy changes as work is done against those forces holding them together. So we're just trying to separate the forces. We're not giving them any more kinetic energy. We're just trying to give more potential energy. You can think of it as stretching a rubber band and pulling that rubber band until it's really tight. Then when it breaks, that's when you end up with the kinetic energy. But you've got to stretch the rubber band and get it before it breaks, and then that way you have that potential energy. That's kind of the best way to think about it. For example 14.7, you have a jewelry designer planning to make some specially ordered silver charms. The melting point of silver is 960.8. They want to know how much heat does the jeweler need to add to half a kilogram of silver at 20 to be able to pour that silver into charm molds. So first we have to heat it to the melting point, then add more heat to actually melt the silver. So here's our equation that we need for this one. We're just taking that silver, we're heating it up, and then we are adding enough energy in this portion to actually turn it into a liquid. So Oops, let's back up for just a second here, and let's go ahead and do this problem. So we know that the temperature change here is 960.8 minus 20. So we started at 20, we've got to get up to that 960.8, so that's a change of 940.8 degrees Celsius. Our Q here is equal to 0.5 kilograms times that 0.235 kilojoules per kilogram degree Celsius. That's our specific heat. So there's my MC, so there's my MC delta T, which is 940.8, sorry. And I'm going to take that and add it to my MLF, which is going to be 0.5 times 88.3. So I'm going to put times here, times 0.88.3. When you do that, you should end up with 110.5 kilojoules plus 44.15 kilojoules, and that's equal to 155 kilojoules of energy in order to raise the temperature of the solid silver up to its melting point, and then to convert all of the silver, that half kilogram silver, into liquid. And so that'd be 155 kilojoules. So there's your first problem. Second problem is you have ice cube trays. They're filled with half a kilogram of water at 20 degrees Celsius and placed in the freezer compartment. How much energy must be removed from the water to turn them to ice cubes at -5? So first we have to cool the water to 0, then we've got to get it to ice. Now that it's frozen, the ice continues to cool all the way down to -5. So the steps that we need in this process, we need to first think about, let's do Q1 is going to be taking that water. So we're going to do MC for water, delta T, for that first temperature change. So the temperature change here is going to be final 0 degrees Celsius. Our original is 20, so we're going down 20 degrees Celsius. My Q2 is negative MLF. So remember, we are, in order to make ice, we're removing heat. So this is negative. And then we want to remove even more heat. And so this is MC of ice times delta T2, where my change in the temperature of the ice, it's going to get to -5, and we start at 0, so that would be a 5 degrees Celsius drop. Now we can go ahead and say Q is equal to M, so that's the mass. We've got the specific heat of water times that first temperature change minus the specific, the latent heat of fusion plus the specific heat of ice times the second temperature change. So all I did was just take out that M. So this would be MC delta T1 minus MLF plus MC ice times delta T2. If we go ahead and actually plug all of our numbers in here, I think what we'll need to do is go ahead and get rid of this. We've got C of water times delta T1 is equal to 4.186 times that -20. That would be -83.72. That'd be kilojoules per kilogram. We have LF, which is, that's latent heat of fusion for ice, for water, I guess, 333.7 kilojoules per kilogram. And then we take C of ice times delta T, and that's equal to 2.1 times -5, and that gives us -10.5 kilojoules per kilogram. So now we can plug everything to that equation that we just wrote out. So this is Q is actually equal to, I'm not sure what that is. So Q is equal to, here's my mass, 0.5 kilograms. Then we have -83.72. So that's the taking that water and removing enough heat to make it ice. Then we're going to take the ice and we're going to take the water and make it into ice. That's what this is. And then we need to go ahead and reduce the temperature of the ice down, and it takes this much energy to do that. So when we're done, we should end up with -214 kilojoules. That just means I have to remove 214 kilojoules of heat. So 214 kilojoules of heat flows out of the system. And that system would be the water, which then becomes ice. So that is a really good problem to do to help us make sure you understand what's going on. Phase transitions, a useful tool for studying phase transitions is the phase diagram. And it shows if you increase and decrease pressure and increase and decrease temperature at those various pressures, kind of what phase these things would be in. So if I do just standard atmospheric pressure, for the freezing point of water, notice it is 0, and the boiling point would be 100 as long as I follow these curves. This curve is for the fusion of a substance, so going from a solid to a liquid, or a solid to what we call fluid here. If I want to go from a liquid to a vapor, we would use this line right here. And if I want to go from a solid right to a vapor, we can actually do that. We call that sublimation. But you do that at you'll notice that you do that at very low pressures. Very high pressures, you'll notice that you can go from a solid to a liquid pretty easily. And so all this diagram really helps us do is to kind of see where all these transitions can take place at different pressures and temperatures. So since the going from one state to the other really does depend more than on just temperature. There's a point to which water can exist in all three forms, where it can have something called a triple point, and that is at 0.006 atmospheres and at about 0.01 degrees Celsius, and so we would call that the triple point. But other than that, that's your diagram that we call a phase diagram. So the curves basically show us the demarcations between a solid, liquid, and gas. At the triple point, we said that they all can coexist, and vapor pressure curve ends at the critical point. And so here's that critical point again. You'll notice that for most substances, you'll see this curve. So you'll come up to the triple point, and then it's basically just a straight line for the fusion curve. This vapor pressure curve does curve a little bit, but not as much as our sublimation curve. And then we do have our critical point out here, where things just become kind of this weird kind of plasma state, I think, as kind of what you can think of it as. The unusual phase diagram of water, you'll notice that this curve kind of backs off a little bit instead of coming up this way. And so this is kind of responsible for some of the unique properties of our good friend water. Thermal conduction is the next thing. This just takes place within solids, liquids, and gases, and conduction is just due to the collisions between atoms and where you have exchange of energy. So conduction is just the transfer of heat along some sort of surface. It also occurs between objects that are in contact. So this is just going from one molecule right to the next. So here I've got the hot side of an aluminum block, and I've got the cold side, and I have heat moving from one to the other. Maybe have an aluminum bar here. It's in contact with the flame here from the propane torch, and then that will transfer heat over to the cold side. So we always have the conduction always moves from hot to cold. Fourier's law of heat conduction, this P, you can think of it as power. And this is kappa. It is the thermal conductivity of a material, how well it can move heat from one place to the other. A is the surface area, delta T is the change in temperature, and D here is the thickness or the length of a material. So it's pretty easy to do. Delta T over D is what we call the temperature gradient. So this thing right here is temperature gradient. Don't let the weird looking symbols fool you. This is a pretty easy equation to work with. This is just another way of looking at it. We can also say that this heat conduction is equal to, we've got our original equation. If we solve it again for the change in temperature, we'll notice that D over Ka is what we call thermal resistance, or how hard it is to have heat transfer from one place to the other. And thermal resistance can be D over K times the area. So if I want to think about maybe insulating something, I want this value to be pretty high. So we think about this in R values. If you've ever bought insulation, you think about an R value, that's what this is, and that's why that's pretty important. So I can look at thermal conduction through two or more materials in series. So I have a couple of different materials here. I've got T1, I have temperature 2 on the inside, and temperature 3 over here. And we can see kind of how that temperature can change over these distances. So that's basically what this is showing us. Remember, R is the insulating value of a material. So for a lot of different layers, here I can say the change in temperature is equal to that power quotient that we had times the sum of all those different layers of resistance. So you might have a wall. So if you're building a wall in a home, you might have the outside of the wall. This might be some styrofoam, and then outside of it you might have either brick or you'll have some sort of siding. And then on the inside of that you'll have maybe a piece of wood for the structure. Oops. And then on the inside of that you might have another layer of drywall. And so each one of these has a different R value, and we would just sum those R values up and we could tell how well your home is insulated. So that's kind of where all this is going. We have a window pane now, so here's a good example. It measures 20 centimeters by 15 centimeters, and the glass here is about 0.32 centimeters thick. The temperature outdoors is negative 15 degrees, and the temperature indoors is a nice room temperature of 22 degrees Celsius. They want to know at what rate does heat leave the house through that one small window. So here we go. Let's take a look. We know that the temperature change here is about 37 degrees Celsius. It's because this is negative. It's the final minus the original. And so this number, 37, comes from that. Thickness of the window pane is about 0.32 times 10 negative second meters. The area of the window pane is about 0.03 square meters. The thermal conductivity for glass is about 0.63 watts per meter Kelvin, and the rate of heat flow is our p-value here that we have. And I'll show you how I like to write this one so that it stands out from kind of the other power that we've been doing. First thing I would do is go ahead and find out our delta T over D value. So this is a 37 degree temperature change, and our D value here is 0.32 times 10 to the negative second. So that's that thickness of that material, and we end up with a value of 1.16 times 10 to the fourth, and this is a Kelvin per meter. So when we write the P, I always write it and then kind of put this funny tail on the end. That helps. My kappa, I try to make this end of my K a little bit bigger, and then I have area times the change in temperature over the thickness, which we've already solved for. So this is 0.63. We're going to multiply that times A, which is 0.03. And then we're going to multiply that times our delta T over D, which we already did up here, which is 1.16 times 10 to the fourth kelvins per meter. And we end up with, now remember, power is measured in watts, so this is no different when we do this one. So that's about 220 watts. For going on in this one, we'll notice that thermal conduction and accurate calculation of the energy loss through a single pane window must also take into account the stagnant area of air that's kind of right up next to the window itself. So the temperature gradient across the glass is pretty small compared to what it is for this air here. So in fact, much of the thermal resistance of a window is really the stagnant air that's on the outside of the two panes. A single pane window is not very efficient, so we're going to replace it with a double pane window, and we put an air gap and usually put argon gas in between the two, and it's got really nice R value, and so it can really hold the heat into the home a little bit better. So the inner surface of the inner pane is at 22 degrees Celsius, and the outer surface is at negative 15. They want to know what is the new rate of heat loss. So we're going to find this new rate of heat loss and see if it's any better than that 220 watts that we had before. So to do this one, we're going to need to start by saying R1 is equal to D over that kappa times the area. This is 0.32 times 10 to the negative second meters. All over, here's our 0.63 times, this is for glass, times that 0.03, and that's the area of the glass, and that gives me 0.169 Kelvin per watt. For R2, this is going to be for the air that's in between, so this is D over our value constant times A, and that's equal to 0.5, oops, this is 0.5, so thickness of the window times 10 to the negative second. This is the air gap on the inside times 0.023 times the area, which is 0.03 again. And this one is 7.246 Kelvin for every watt. We know that R3 is equal to R1, so we're going to add all these together. So R1 and R3 are the window pane itself. So let's just draw a picture here really quick. So here's the two panes of glass, and then on the inside of that we would fill it with a gas, clear gas of course, so probably argon. So we have two panes of glass, that's my R1 and my R3, and then my R2 would be that argon gas that's in the middle, and that's why we have this K value is that. So let's go ahead and sum all these together. So the sum of the R values are equal to 0.169 plus 7.246 plus 0.169, and we get 7.584 Kelvin per watt. So now we can use our P equation again, our funny P. Well, that's too funny of a P, I guess. So here we've got our funny P for power. It's Q over T, delta T, which is equal to delta T over the sum of my R values. And that's equal to 37K, that's my change in temperature, over my new R value, which is 7.584 K over W. And that's only equal to 4.9 watts. So huge savings in energy when you have a double pane glass that has that air gap in between the two. Next section is about convection. This just involves some fluid currents, and they carry heat from one place to the other. So in conduction, energy flows through the material, but in convection, the material actually moves itself from one place to the other. So if you live near the coast, you get an ocean breeze that cools the coast. The water, the air warms, it cools, it expands, and then it falls. When it falls, it then goes through that cycle again. At nighttime, the cooler air falls, and then you get a land breeze coming out on the ocean. It warms, cools, and then falls back down. So that's why anytime you live on the coast, you have pretty mild temperatures. If you think about San Diego or Los Angeles, temperatures there are really nice year-round for the most part. And it never gets too hot, never gets too cold. And this is kind of why. Natural and forced convection. In natural convection, the currents are due to gravity. So a fluid with a higher density sinks and then becomes more buoyant as it gets warm. That less dense fluid rises. So in forced convection, the fluid is pushed around by mechanical means such as a pump or a fan. So your heating system in your home does that. If you have a fan in the ceiling, the fan is nice because you can either push heat down or you can pull heat up and make it come down the wall. So it's kind of a nice little system that happens there. The last section here is called thermal radiation. So all objects emit a little bit of energy through electromagnetic radiation just because in your atoms the electrons are kind of vibrating up and down. Thermal radiation consists of these waves. They do move at the speed of light, and unlike conduction and convection, it does not require a material medium. So we don't have to have air, so there's no air currents there, and there's nothing solid that it moves through like a bar. Or anything similar to that. So an object emits thermal radiation while it absorbs some of the thermal radiation emitted by other objects, and that is thermal radiation. The Stefan radiation law basically just says that an ideal body that absorbs all the radiation is called a black body. This black body absorbs not all visible light, but infrared, ultraviolet, and all other wavelengths of electromagnetic radiation. So it turns out a good absorber is also a good emitter of radiation, and a black body emits more radiant power per unit surface than any other real object at that same temperature. This is the power equation for it. So remember, we're just looking at how this is going to emit some sort of radiation. It's equal to this funny looking symbol here, sigma. Sigma is equal to 5.670 times 10 to the negative 8. This is a constant. And then we've got area, and then this is our temperature in Kelvin to the fourth power. So since real bodies are not perfect absorbers and emit less than a black body, we define emissivity, so that's this E, as the ratio of emitted power of the body to that of the black body at the same temperature. So when we do this for real objects, we're going to use this equation, and there is a E value for each one of our objects. So this just shows the relative amount of radiation at different wavelengths, and so as you increase the wavelength, you'll see that at a point we're going to get a maximum here of for a 1.45 micrometer wavelength versus a 1.9 micrometer wavelength. You get a little bit different, so these are a couple curves that show that. This lambda max, this is the wavelength, maximum wavelength times temperature, should be equal to 2.898 times 10 negative third meters times a Kelvin. This is where T is temperature in kelvins, and wavelength maximum here is the maximum radiation wavelength in meters. And this is what we call Wien's law. The maximum rate of energy from the sun occurs in the middle of the visible range, so your wavelength here is about 0.5 micrometers times 10 to the negative 6 meters. So they want us to estimate the temperature of the sun's surface. So we can assume that the sun is a black body. If we do, then the wavelength and the surface temperature are related by Wien's law. And to solve this one is pretty simple to do. This just looks very difficult, but it's really a pretty simple plug and chug as we go through. So I know that my wavelength maximum here is equal to 0.5 micrometers. That's equal to 5 times 10 to the negative 7th meters. So because it's 0.5 micrometers, I have an additional place that I have to move it. So here I'm going to say the lambda max times T is equal to 2.898 times 10 to the negative third meters times a Kelvin. And so our temperature on the surface of the sun is theorized to be 8.8 times 10 to the negative third divided by that that lambda max, sorry, it's not alpha, it's lambda, and that's 5 times 10 to the negative 7th meters. And this is meters times a Kelvin, so your meters cross off, and the temperature is 6,000 Kelvin. So that's kind of what you'll see for the surface temperature of the sun. Moving on, this is simultaneous emission and absorption. So remember we said that an object can both emit and absorb thermal radiation, has a net rate of heat flow. So I have an object with a surface area A and temperature T. It's bathed in thermal radiation coming from the surroundings that are uniform, temperature Ts. Then the net rate would be equal to the equation you see here. So all I've done is I've just used my second equation that we went through earlier in the thermal radiation section, and I'm just finding the difference between the two to find that net rate. And I can factor out the E, this symbol times A out. Okay, so E sigma out times the area out, and I get T4 minus the TS, which is that uniform temperature of the surroundings to the fourth. So the emissivity here just measures not only how the object emits compared to a black body, it also measures how much the object absorbs compared to it. So emissivity here really just depends on temperature. So our equation assumes that this emissivity at temperature T is the same as it is at temperature Ts. So if these two temperatures are very different, we would have to modify the equation and use a couple of different E values. But for what we're doing, we can use the same one every time. Last problem, this one, a person in body surface area of 2 meters squared is sitting in a doctor's office with no clothing on. The temperature of the room is 22 and the person's average skin temperature is 34. Skin emits about 97% as much as the black body is the same temperature for wavelengths in the infrared region where most of that emission occurs. So they want to know what is the net rate of energy radiated away from the body. So here we go, everything we're given, 2 meters squared surface area. The T value here of the room is 22, skin temperature is 34, and the fraction of energy emitted is about 0.97, so that's our emissivity value. They want us to find the net energy rate transfer. So here we go. We're going to say that our temperature here is 273 plus the 34, and that's 307 K. TS for this one is equal to 273 plus 22. That's equal to 295 K. And so the net here is equal to E times sigma times the area, and then we've got T4 minus T to the fourth, and that's for the S. So we're going to have P net is equal to, now remember we set our emissivity here as 0.97. We're going to multiply that times 5, 0.67 times 10 to the negative 8. So we had to look that value up. We have 2 square meters, and then we have our temperature change, which is 307 to the fourth minus 295 to the fourth. And that's going to give us 140 watts. And that is the end of that problem. Let's go ahead and take a look at this last problem. So this is radiant energy from the sun reaches Earth at a rate of about 1.7 times 10 to the 17th watts. So that's our power value. So that's this value. An average of about 30% is reflected and the rest is absorbed. So energy is also radiated by the atmosphere, assuming equal rates of absorption and emission, and that the atmosphere is a black body. So we could say E1, E here is equal to 1, emissivity. Calculate the temperature of the atmosphere. The sun's radiation peaks in the visible part of the spectrum, but the Earth's radiation peaks in the infrared due to its much lower surface temperature. So let's go ahead and take a look. So Earth must radiate the same power as it absorbs. We can use Stefan's law to find the rate at which the energy is radiated as a function of the temperature. And then we can really just look at that and see how it equals the rate of energy absorption. So here's kind of what we do. We're going to say we know that the p-value here is 70% of 1.7 times 10 to the 17th. That gives us 1.2 times 10 to the 17th watts. Your p-value, remember, is E times sigma A times T to the fourth, where our area here is 4 pi times the radius of the Earth squared. That's what this is. So T here is equal to, we're going to solve this for T. So we have to do the fourth root. That's why we've taken it to the 1/4 power. We're going to replace this A with what we have here. And so now we're going to say the temperature is equal to, of the atmosphere, is equal to that power value that they gave us divided by the emissivity, which we said is 1, times sigma, times 4 pi, the radius of the Earth squared. And then we're going to take the fourth root of that. So we're going to plug everything in, 1.2 times 10 to the 17th watts, over 1 times 5.67 times 10 to the 8th watts per meter squared times Kelvin to the fourth times 4 times pi, and then here's the radius of the Earth. We'd have to give you that number and we square it. Once you find that answer, you take the fourth root and you end up with 253 K, which if you do your math should be negative 20 degrees Celsius. Thermal radiation, this is the last thing that we'll talk about. This is just global climate change. This is why we worry a little bit. We know that from the sun we get infrared energy. We also have UV comes in and the ozone blocks it pretty much. Otherwise we'd be burnt to a crisp all the time. Everything would die, we'd be in trouble. And then visible light gets through that atmosphere. So the atmosphere and the ozone in the atmosphere really blocks that off. If we have a thin enough atmosphere, we get a lot of that infrared, which will kind of come out. But the problem is as these CO2 gases and things kind of get a little bit thicker, we will hold more of that infrared radiation, and that's heat. And that's where we get in a little bit of trouble. So whether you think it's man-made is predominantly the factor, or if you think these are just cycles that we're going through, it doesn't really matter. It's just the physics here just shows you kind of why all that heat gets trapped. Similar to at night, if the clouds are out, you trap more heat. It's not as cold in the morning as it is on a nice, clear, starry night. You release a lot of that infrared radiation right back out. It gets reflected right off their surface. And that is the end of this section.